Good morning, everyone. Welcome to the Tuesday Refresher. This is Jim Chastain with EasyPower Applications Group. I want to talk today about relays, transformers, and coordination. We've had several questions about various aspects of this, and so we're going to do a real quick refresher on it. The agenda for the most part is to demonstrate the use of EasyPower Power Protector module in setting up relay protection primarily for transformers, the main transformers and substations, and then coordination with other protective devices. Most of this discussion is based on industry standards and its acceptable practices. That means it doesn't constitute an ironclad procedure, but more of a way to illustrate how to utilize EasyPower tools to make the engineering judgments that's required on most complex systems. And then in addition, I want to emphasize the value of what can be gleaned from utilizing smart PDC in the process. So welcome one and all. Coordination itself, when we're talking about coordinating loads and isolating remote loads as close to the fault as possible, we generally start in adjusting low voltage power circuit breakers at the load and then gradually slowing the upstream devices up as we progress up the one line. And it's different with relays. Pretty much you start at the top and then you try to coordinate as you move down the system. And the reason for this is that we basically set on the very first relay an instantaneous protection that is guaranteed to keep whatever fault, if it exists, away from the transformer. So the idea is to protect the equipment as much as possible, and we'll kind of see that as this develops. In ANSI C57.109, and likewise in ANSI C57.112.59, there's a description of damage curves and how to plot them on TCC graphs that express the need to avoid thermal damage at the longer time runs and mechanical damage at the higher impulse current values. And these, again, are guidelines that are based on informed engineering judgment and historical field experience. So there's no rules as far as drawing the curves. They're recommendations, and that's what's reflected when we get into the TCC plots for EasyPower. Now, in transformer protection, the gold standard for internal fault protection is pretty much differential relays. And there is a number of variations, but they're all primarily ANSI code 87, and they can include restrained or unrestrained settings, either in comparison or differential in phase differences or in absolute current differences. The main advantage is that they can, because they null out the normal or regular current in the system, they can be set to respond to very small differentials between the incoming and outgoing of the protection zone. And as such, it's difficult to model the current aspect of the protection. And so in EasyPower, we simulate the time response for a bus that's protected by the relay breaker combination. So we'll show that as we get into setting those relays. Then as a backup for this gold standard, very frequently most systems will utilize phase over current relays as backup, and this is a more traditional TCC plot utilization, and we will go through the setup of a phase over current relay and how that serves to protect both for through faults and internal faults. A real quick side note about internal fuse protection. The question came up, do the internal fuse protections in transformers affect arc flash calculations? The answer is no. They're there strictly to prevent the worst case mechanical failure of the transformer and to try as much as possible to prevent fires or explosions. And so they're fuses that are set to really last a very long time before they blow. So that really won't come into the conversation. Okay, now in EasyPower, the way we simulate a differential relay is we calculate the time delay that the relay will exhibit for whatever difference criteria we've determined for our system. And then EasyPower will determine what that time element or how that will affect the incident energy calculation, assuming that's the system that clears the fault. Now, again, the zone of protection can be very wide or very complex, and it determines primarily by where the CTs are set up. And as I mentioned, they're wired to null out regular current, but as such, they're very fast in their response. Here we have CTs. Now, you can set up the zone of protection across a transformer, across switchgear, across some number of complex systems, but at simplest form, it's primarily transformer protection. And what we're monitoring is incoming current to the transformer and then outgoing current. And this will determine the CT sizing that we are going to use, the configuration, whether it's delta Y or delta delta. And again, the relays themselves can accommodate these variations. And so it's important to make sure we have an understanding of what's been set up in the system. But then once that's attained, in this case, we're going to be making adjustments on R7, which is a Basler relay. We go to the manual or the data sheet, and in this case, this is the Basler B187. We see for the operating current, there's an association between the number of multiples of the pickup. So we're going to assume that we have a 2x the pickup in use in our application, and at that point, we should see a response of the relay at something better than 50 milliseconds. So just to make round numbers, we're going to assume 50 milliseconds is a response time that the relay will reflect once our threshold is met for the difference between the inputs and the outputs. At that point, then we need to go into, in this case, EasyPower and get the reaction time for the breakers itself. So let's go into EasyPower. And in this case, we've got the relay set up to trip BH1. If we go into the database edit, we see we've collected data. It's a G, manufactured, HP type, style, and amp that it's set for. And once we've set up that part number, then we should see a number. We want to see these numbers change. So these will all be 0 when we first set it up. And when we calculate, the fact that these numbers change means it's found that data sheet, this part number that we gave it in the device library. And this breaker is guaranteed within these span of parameters to be able to interrupt the circuit within 3 cycles. So at that point, we want to know what the time element of 3 cycles is. Let's go into our calculator, take 3 and divide by 60. And we see that that's a 50 millisecond time delay. So we have 50 milliseconds for the breaker to open and 50 milliseconds for the relay to respond. So in EasyPower, we go into the database edit for the bus that's within the zone of protection, or that's being protected, if you will, by the zone. And so if the upstream breaker to this bus trips, we want it to respond to a user-defined time. So normally this will be set for TCC auto calculate. We're going to set it up for both user-defined time and TCC calculations because we're going to have an overcurrent relay as well. So we show R17 is the upstream device. The response function is going to be, or the relay function is going to be 87. And then the time that we determined is 0.1 milliseconds, which is 50 milliseconds relay time and 50 milliseconds interrupt time, breaker opening time. So let's save this. All right, so that takes care of our differential relay. Next, we're going to set up this as a backup, this overcurrent relay, phase overcurrent. And to do that, first of all, we want to determine our maximum full load current for this transformer. Full load current for the transformer. To calculate the full load amperage for a transformer, we take the MVA rating, divide by the square root of 3, and then divide that again by the kilovolt rating. So the main transformer in this case is 115 kilovolts on one side, 13.8 on the other, and 8% X over R. And it's rated for 20, let's say 30 MVA. And so if I put all that into my calculator, it turns out like this. So we take 3, take the square root, save it in our repository, take our MVA rating of 30, divide that by the square root of 3, and then divide that by the voltage, which is 115 kV. We get 150 amps as the maximum full load current. Now, this doesn't take into account transients. There could be, and it doesn't take into account inrush for that matter. So as a rule, you want to set this some percentage higher. It can range anywhere from 10% to 40%. And so let's add 10% to this number. Okay. Let's try that again. 150 times 1.1. So 165 is what we're shooting for. Let's go back into EasyPower, open up the relay. Now again, we've set up the GEIAC 53. It's a single unit. It's set up to activate the BH1 breaker. And we want to set it for 165 amps, which is just a little bit more than 4.1, and I don't think it's going to let us get there. So let's stay with 160 amps. Now, the things we're looking at for through fault damage is protection in the thermal damage range and the mechanical damage range. And then the max current in the primary that could be felt from a downstream fault will be what we use for instantaneous. Now, the standard acceptable applications that are recommended for both adjustable low voltage power circuits, relays and breakers suggest that for transformers we want to use a very inverse curve. And then the NEC suggests for certain transformer values, whether it's unsupervised or supervised, and size, we want a maximum setting over the full load value. So for 6% and less, over 600 volts, we want a maximum setting of 6 times the full load rating as our upper limit. And so we'll come back to this a couple times. Now we do know from EasyPower that if we go into short circuit and fault this bus, the maximum fault current, 3-phase bolted fault current that this bus will see from the transformer is 9,301 amps. the maximum current that will be received or seen on the primary side is just over 1100 amps. So we can, with a fair amount of confidence, predict the maximum current that a through fault will generate is something less than 1200 amps. So we just bump this up by 10%. So we can set an instantaneous value then for this relay at 1200 amps, because we know anything greater than that, there's a fault on the primary side, and it has nothing to do with the secondary side. So that's where we'll set our instantaneous rating. So now that brings us to the point in our database edit of setting up the values for the relay. All right, so we've got 160 amps for our tap setting. We have very inverse for our curve. We're going to pick out a medium value here until we actually see where the knee in the curve is. So let's leave this at 4. And then our instantaneous trip, we can set this for 1200. And I think if we kind of hunt and peck a little bit, we can see 1200 is a set point of 30 on the CT. All right, so now is it time to look at our curves compared to the transformer damage curves. So we select, go to coordination, and plot the curves. And what we see now is our transformer max full load current is going to be shown down here in my cursor coordinates. And if I center it right there, it shows 1237. It's like, wait a minute, Jim, I thought you said it was 150 amps. Well, it is, but we're looking at the 13/8 side. So I'm going to go back and plot my curve. We're going to change this to 115 kV. And let's put it on a scale of 1, just to see a little bit more accuracy. All right, now when I get to the full load current from my transformer, it is in fact 150 amps. So I want my maximum set point for the relay to be slightly above that. And so here we have it set at 160, which is what I wanted. Here we have our maximum current setting, or instantaneous setting, is at the 1200 amp range, because we know that's any current above that will be no longer a through fault problem. Now, the one thing we've kind of rushed by is the fact that this relay on the primary side is sensitive to inrush current that could be harmonic rich and cause a lot of problems with relay settings. And that all goes to the what's been used for setup of the transformer. Now, in here, we've used a default setting of 8. Some industry pundits recommend using 12x, the full load current rating. And if we do that, we notice that our set point is right on the line and probably will not be sufficient if we want to use 12x as a guideline for our inrush. Other projects, depending upon their application or what information they get from the manufacturer, use 25 times full load current. And once we apply that, we can see that we're way out of bounds as far as being activating our trip based upon the inrush. So whatever standard we use and whatever the manufacturer recommends as the inrush, we want to set for, and this is at 1/10 of a second, we want to make sure our instantaneous setting is to the right of that and will not be affected by the inrush. So let's kind of go back to what we had for 8x and go back to our 1200. 1200. All right, so the thing we haven't adjusted is the dial setting. And this has to do with the knee and the curve. Now, one thing we haven't touched on, and that is usually you see two curves. One's the 100% damage, and the other's the 58% damage curve. And that's due, in this case, it's due to the fact that we have a non-hardwired or solidly grounded transformer. And so with some resistance in this neutral leg, the effect of having a single line to ground fault will be generating currents much less than the range we're talking about for fault currents here. So if we were to go back to our impedance and take out this resistance, it would show up the other curve. Nevertheless, we want to be mindful of the frequent fault curves for both hardwired and resistance grounded. And if we need a certain amount of separation, we would use this dial adjustment to make the clearance. And let's say we're happy with that. So now what we've done is we set this as a fallback or as a backup. It too will be activating BH1. And now as we go back to our short, I'm going to close this. Go back to our short circuit focus. We're going to fault the bus, single bus. And we're going to look at the arc flash results. And we see two elements here for that bus faulting. One element is R18, which is our backup phase over current. And if it trips on phase over current, it'll respond in 1.5 seconds, and it'll give us 58 calories exposure. May not be adequate for our purposes. On the other hand, if the arc is detected by the differential relay, then it'll give us a 3.2 calorie exposure because it's reacting in 1/10 of a second. Now, just as a point of order, what I mentioned before was the value of smart PDC as a backstop and seeing what I missed. So I'm going to go back to coordination. I'm going to pick out, let's leave out this one relay because we haven't done it yet. And plot the TCCs. And then invoke smart PDC. And it made some variations in my separation between the fault curves and the plot. Now, more valuable than the one-line diagram or the plots on the TCC is the report that then is generated by Smart PDC. And it tells me specifically what it was coordinating that relay with. So here's where our max settings of four times the FLA, and on the secondary side the max settings 250% because it's at a lower voltage. The relay was clipped, and so it's recommending that we have a time dial of 4 because it meets the minimum requirement of 0.283 seconds, which I failed to navigate when I was doing the setup. So again, the point is that this is a backstop in creating my report. Now, when we move on to the phase over current relay that's being used in the secondary side, we have a couple gears to shift. One is we're looking at a zone of protection for this relay to be different than from either the phase over current for the primary side or the differential. And it also emphasizes the fact that we have overlapping zones. In this case, we're looking at protecting the switchgear and the cabling down to the next level of protection. And at the same time, we want to establish or make available the full amount of buffering that the transformer allows on the secondary side. So again, we know from the short circuit study, the maximum current in the secondary side from a fault is 9,000 amps. On the other hand, we can see in the power flow that in the power flow analysis, I'm going to look at my current in each of the branches. A typical current for this system is 165 amps. So we don't have to come anywhere near 9,000 amps to protect this circuit. Anything over even say 10 times this value is perfectly adequate in terms of fault protection. So that's when we go back to our phase coordination. We look at these elements. We plot the TCCs, and we can see now that this Basler R4 is set up to protect a number of elements downstream, and where the maximum current is set or maximum trip is set is only 281 amps, which is roughly twice what our full load current, not our full load current, but twice what our normal current is in the system, but far short of the 9,000 amps. The other thing we don't need is an instantaneous trip, because that's being handled by the upstream relay. And so now we don't put an instantaneous trip in the downstream relay. So at this point, it's worthwhile taking a view of what Smart PDC would give us and looking at that report. And you can see here that we have okay, we didn't rate the main bus, which is one of the things it's trying to protect. So it's silly not to have that information in our database. Full load primary current is 53 amps. The secondary full load current is 1549. And so the maximum settings per the NEC recommendations is 6x on the primary, 125% on the secondary. And then we're saying here that there wasn't selectively coordinated because the gap of 10% wasn't met at the top. And it gets into overlapping the zones down in the transformers in the lower part of the circuit. Now, clearly, these aren't hard and fast regulations, but they are good influences, and considerations should be taken for as far as serious settings, because the tool is looking at far more than we can look at in the one-line diagram. All right, we're going to try to go through the same process with the lower transformer, and then try to iron out the crossover between the two. This lower transformer is a 1.2 MVA, 13.8 to 480, and calculating the full load current, we'll take the MVA rating, divide by our square root of 3, and then divide that by the 13.8 primary voltage. We see the full load current's 50 amps. If we go ahead and go into coordination, well, before we do that, let's find out what the max current is. Go into short circuit, fault the secondary bus. We see the maximum fault current for a through fault is 650 amps. So somewhere between 50 amps and 650 amps, we need to find a set point. Go into coordination, plot the curves for the relay and the transformer, we can see that our full load current, and again, we're on a different scale, so let's put this up to 13.8. And dial it down to scale of 1. All right, so the full load current for the transformer is indeed 50 amps. So we can see here. Here's our set point for the relay. And I'm going to start with Smart PDC just to kind of get a reference. They're recommending the relay be set at 181 amps, which is about halfway between the 50 and the, well, not even a third, between the 50 and 160 amps. And then it's trailing off with no instantaneous set. More valuable then is to look at the auto coordination report and what's being described here. So again, it's looking at the cable capacity, the transformer itself, full load current, and maximum full load current on the secondary. Looking at 125% on the secondary side of 1900 amps, and then where the low voltage breaker will be protecting the motor downstream. And so what the recommendation is then at a set point of 181 amps with a time dial at 0.8, and then no instantaneous setting and a maximum delay. And if we go back to our plot, that's pretty much, we've got the capacity to protect the cable. We are protecting most of the thermal damage curve, most of the mechanical damage curve, some of the thermal damage. But like the report was telling us, if we go back and include the operations of the downstream breaker, we can see that the breaker will take up some of that slack, and then the relay won't even be close to the inrush for the transformer. I guess my point is there's no hard and fast rule here. This is a series of recommendations, and quite frankly, it's nice to have Smart PDC make some of these recommendations. It's worth looking at the settings that are available in Smart PDC options. And what we keep referring to is the transformer NEC requirements. And again, the tool is going to enforce these and not allow us to make a setting beyond the limits here. But we can, with certain restrictions, be able to move past one setting on the NEC limit table if we're using low voltage power pickup units. So I think I've done about as much damage as I can do on this. I don't think we exhausted the topic at all, but I think we gave some insight into using Power Protector to setting up relay protection for transformers, both in the primary side of the world and in the feeder substations, and the importance of referring to the analysis of the Smart PDC module if you have it available. Hope this helped you out. Appreciate your attendance, and any questions that are submitted during the session we will answer via email. Thank you very much for supporting EasyPower. Have a good day.